Hello, I'm Abhinav, and I'm going to present our work, Not Made for Each Other, Deepfake Detection Based on Audio-Visual Dissonance. And this is a joint work with Komal Chugh, Parul Gupta, and Ramanathan Subramanian.
In this work, we propose a pipeline for detecting if a video has been manipulated or not. So these videos which are edited or manipulated using AI-based techniques such as generative adversarial networks are being referred to as deepfakes these days. Let's look at another example of a deepfake.
Instead, only try to realize the truth.
What truth?
There is no spoon.
There is no spoon?
So usually either the identity of a subject is changed in a video, as you can see in this example, and the face of the new person is embalmed onto or warped onto the original subject. In some other cases, deepfakes are generated by changing the facial movements and the audio of the same subject. Now, these type of manipulated data has some serious repercussions. For example, one could run misinformation campaigns using this fake data. Further, during sensitive times such as elections, deepfakes can be used. And it has been observed recently that trolling is happening online by generating these deepfakes. Further, with the effect of newer sophisticated deepfake generation methods, it is possible that it will get difficult to figure out for a layman that if a video is real or fake. And what this could lead to is loss of faith in media. Now, let's look at some of the techniques which have been proposed in the recent past for detecting if an image or a video is real or fake. So earlier methods are based on analyzing the visual artifacts in a face. So Materna and others proposed a network pipeline which exploited the potential change in the color of the eyes which may occur during the manipulation of a video. Further, they also found that the region of the eyes and the region of the mouth can give some vital cues about if a video has been manipulated or not. Then Yang and others looked at the change in the head pose, essentially the inconsistencies which may occur in the head pose in a video when it has been manipulated. Further, Lee and others, they found out that the eye blinking attribute can be used to predict if a video has been changed or not. So essentially, they used a long short-term memory network and they tried to predict if the eye blinking rate can be modeled and further if a video has been changed or not. Further, Lee and others in their other work, they proposed an interesting idea. They said, well, generally in most of the cases, manipulated face needs to be warped onto the original face. And in that warping process, there could be some anomalies in the transformation. So they generated negative data by changing these different warping techniques. And they found out that even standard architecture such as ResNet could be used to predict if in an image manipulation has been done to a face or not. Further, Nguyen and others, they proposed a capsule network based approach to detect if there is any manipulation, and they got really encouraging results. Further, Sabine and others proposed the use of recurrent neural networks for predicting if a video has been edited or not. Our work is different from this, and it builds upon these prior works in the sense that we are investigating audio and visual based techniques for detecting if a video has been manipulated. So the hypothesis of our work is that if there is any manipulation in audio or visual modality, this will lead to disharmony between these two modalities. For example, if there is manipulation, then it may lead to observations such as loss of lip sync. There could be unnatural facial and lip movement. And this could be leveraged on by a network to predict if there is a manipulation. So our work is inspired from the seminal works of Grimes and others. So Grimes did a psychophysical experiment to study if the effect of dissonance is noticeable. That is, there is if the audio or video has been manipulated, will the user notice that in the case of a TV? So essentially the TV advertisements were the use case in this. So we also hypothesize that if there is a change which has happened in either audio or video, then the sync between audio and video, that would be disturbed. And that can be used to predict if a video has been manipulated or not. So now let's look at our pipeline. So at the top, we have the video, and here we have the audio of one sample. We divide the video into segments and the audio into audio segments of the same duration as the video. On the video chunk, we apply phase detection and we input this region of interest into a network. Now this series of convolution layers then further are fed into a fully connected layer. And in parallel, from the audio segment, we extract the MFCC features. And the MFCC based feature is input into the audio channel. Further, when we reach the fully connected layer, we actually add a contrastive loss. And we also have two other losses for the individual channels. Now let's discuss the training strategy. We input the video segment of D seconds into the visual channel and the corresponding audio segment into the audio channel. The first loss function which we use during the training is the contrastive loss, which is based on the dissimilarity score, which is computed between the weights of the fully connected layer of the audio and the visual channel. Further, to increase the discriminative ability of the features which are being learned in the audio and visual channel respectively, we add the cross entropy losses. So we add one visual cross entropy loss for the visual channel and a audio cross entropy loss for the audio channel. So the final loss function for the training is a combination of these three losses. Now during the test time, we again segment input video into segments and we compute a dissimilarity score between each audio and video segment, which is this term. And later the modality dissonance score MDS is the final score, which is used to predict if a video is real or it has been manipulated. Now for the data sets, we use the DFDC dataset. Now the DFDC dataset has been recently proposed as a Kaggle challenge, and we used a subset of videos for fair comparison with earlier works. Now the data in the DFDC challenge has been manipulated using different techniques, which makes this dataset quite challenging. The other dataset which we used in our experiments is called the Deepfake timid dataset, which is a subset of an older dataset called Vidtimid. The data in this particular dataset has been manipulated using a GAN network. And there are two configurations for the experiments with this dataset. One is with a higher quality and the other is with a lower quality. So now for deciding the optimum parameters of our network, we did the following evaluation study. So the first is to look at the effect of the different loss functions. So on the left here, I have a plot where the x-axis is the modality dissonance score, the overall score which we get for a video. And on the y-axis, we have the percentage of videos. So here we see that for the combined loss, the distribution of the real videos and the fake videos has a smaller overlap as compared to when we only use the contrastive loss. So the overlap of the modality dissonance score is high when we only have one loss function as compared to when we have the three loss functions. That is, we add the cross entropy loss to the contrastive loss. Further, we also investigated the unimodal distances. So on the x-axis, we have the interpair L2 distance. So interpair means the real and fake for a particular subject. And on the y, we have the percentage of video pairs. So we see that for the audio stream, the distribution is quite skewed here, and it is around 0. And in the case of the video stream, which is the right, we see that the distribution is well spread. So essentially what this tells us is that in the case of this data set, these are done on the DFDC data set, the manipulation is done more in the case of the visual stream, and it is relatively less in the case of audio stream. So here is a comparison of our method on the DFDC and DFTIME datasets. So the metric of evaluation is the video level area under curve. And as observed on the last column, so our method outperforms the earlier state-of-the-art methods by 7% on the DFDC dataset, and it has comparable high performance on the DFTIMIT dataset. Now it should be noted that the later DFTIMIT dataset is smaller in size, and that could be attributed to a higher cost for even a small mistake in the dataset. Now let's look at some qualitative results. So here we have a manipulated video, and on the right, we are going to plot the segment level score. So I'll play the video now.
We're entering an era in which our enemies can make it look like anyone is saying anything at any point in time, even if they would never say those things. So, for instance, they could have me say things like, I don't know, Killmonger was right.
So as you can see here, the plot shows that the dissimilarity score is quite high for this video, as there is a dissonance between the audio and the visual streams. Now let's look at another video which has not been manipulated. And please notice the plot on the right, and particularly the dissimilarity score.
Hi, everybody. Anaya, thank you for that beautiful introduction. I could not be prouder of everything you've done in your time with the Obama Foundation. And of course, I couldn't be prouder of...
So here, as you can notice that the score is lower as compared to the fake video, which was in the earlier slide. Now further, since our approach is based on computing this dissimilarity at segment level, we also evaluated the performance of our method for the task of localizing the timestamps of manipulation. So the task is, where has the manipulation occurred in a video in time? Okay, so for this, we mixed the real and fake segments of the same subject in the DFDC dataset. And as you can see on the bottom here, there is a video which is created by mixing some real segments and fake segments of the same subject. And on the y-axis, we have the dissimilarity score between the audio and visual sample. So we see that the method is able to localize the fake data, the fake timestamps. And also similarly, in this case, when half of the starting video is real and the later half is fake, we see that the dissimilarity score is high in the case of the manipulated video. So let's see how this score is calculated at a segment level for another video in the DFDC dataset. So as we are analyzing at segment level, we see that the score jumps up when we see a fake video clip which is inserted in a real video clip. So in conclusion, we find that the audiovisual dissonance is quite discriminative. And also when we divide our sample into smaller segments, that leads into finer grained results, which can be used for the task of localization. As part of the future direction, we will be exploring weakly labeled based paradigms, essentially how we can exploit multiple instance learning based frameworks so that we can do localization in time as well. Furthermore, we would also evaluate different strategies for fusion of the audio and visual segment. And also, we will evaluate the performance of the method on cross data set. Let's say when we train on the DFDC and test on face forensics and vice versa. So that concludes our talk. And I wish to thank you for listening. And the source code for the method is available on this GitHub link. And please reach out to the any of the authors for any of the queries, and the email addresses are also available on the GitHub link. Thank you.